All right. All right. Has anyone recreated Somewhere Only We Know by Kian? Has someone made a cover of this? Somewhere Only We Know cover. Rihanna? No, I don't want to know. Somebody that is not famous. Yeah, they're gonna give me a strike. Darling. La 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 la.
What if this song?
Oh, simple thing. Where have you gone? I'm getting old at night, and I need something to rely on. So tell me when you're gonna let me la 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 la
on each run of the experiment, he argues that the results in which they are anti-correlated up and down, at least 5/9 of the time, the particles have to have that disposition as opposed to this or this. A prediction that emerges from this view of reality, that particles have definite spins along all of these axes that are being measured. Let me show you how the argument goes. It's quite simple. So if you think about it, there are obviously 9 combinations of possible detector settings. 1 on the left, 1 on the right, 1 on the left, 2 on the right, 1 and 3, 2 and 1. You got 3.
Hey, crazies. Experience with physics has taught us that the universe is inherently local. Each point in space can only affect its immediate surroundings.
So, what is this?
So I was listening to this guy. Which lecture of his? La 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 la. Maybe this one. Leibniz's principle is pretty amazing. La, 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 la. I need to listen to more from this guy. Which is the first video that I heard of him? I think that was it. I'm not sure. Wait a minute. Let's just search Rob Speckens. Maybe it was this one? No, I doubt it. I think it was this one.
Physics, Waterloo, Ontario, Canada. My name is Greg Dick. I'm the lecture this afternoon. PI researchers have a question that you would like me to ask speaker, Dr. Rob's of quantum theory. He received his BSc in physics and philosophy from McGill University and then completed his master's and PhD in physics at the University of Toronto. He held a postdoctoral fellowship here at Perimeter Institute essay book, Quantum Theory, Informational Foundations, and explain why he believes many of today's quantum mysteries are actually the result of category mistake concerning the nature of quantum states. Ladies and gentlemen, please welcome Dr. Rob Speckens.
So he says things that are extremely similar to what I've been saying.
So I wanted to start the talk today by just making a few general comments about the process of doing science. In particular, I want to make an analogy between making scientific discoveries and solving puzzles. So I'm going to start with an example of a puzzle that you might be familiar with, which is Sudoku. Maybe there's a few of you who aren't familiar with Sudoku, so let me just briefly tell you how it works. So you have this 9 by 9 grid of squares. Some of them are filled in with digits between 1 and 9, and your job is to fill in the blank squares with digits between 1 and 9, and you have to satisfy 3 constraints. Every row has to have each one of those digits appearing somewhere once, similarly for every column and for every 3 by 3 square. So over on the right here, I've got the solution to this particular Sudoku puzzle. And although it can be very hard to solve a Sudoku puzzle, once you've got the solution, it's very easy to test that you have got it right, because you just verify that all the constraints are satisfied. And so science is often like this. So you have multiple constraints you have to satisfy that are competing with one another. So if you're doing physics and you're building on some pre-existing physical theory, then you have to, at least in your new theory, reproduce all the successes of the old theory in the domain where the old theory worked well. There are constraints coming from principles of rationality. Your theory should be logically consistent. It should be mathematically well-defined. Those sorts of constraints. You have constraints where you want your theory to be coherent with nearby scientific disciplines. So if you're doing physics, you want it to cohere with chemistry and maybe with computer science. And then finally, there's the constraints that come from experiments, and you need your theory to reproduce the experimental data. But because how you interpret the data often depends on the theoretical framework of your theory, there is some give there. So maybe something that looks like an experimental disconfirmation of your theory ends up not being that if you interpret it appropriately. So there's some leeway in all these different constraints, and your job is to somehow make it all work and get a whole that satisfies all those constraints. So when you're in the midst of it, of course, it looks a little bit more like this. So clearly, whoever was doing this Sudoku puzzle got stuck at some point, and a lot of scientific progress is a bit like this. And usually the diagnosis is that somewhere along the way you made a mistake, and that mistake is propagated forward. You've done a lot of moves. What you've done seems internally coherent, but it's all based on this wrong foundation. And so at some point you get stuck and you can't make any further moves. And so in science, that happens as well. There's fields of science that are built on top of mistakes. We need to correct those to make progress. But there's one kind of mistake that I want to focus in on, which is a category mistake. So this is a particularly egregious type of mistake where you're not just wrong about some entity in your theory. You're even wrong about what kind of entity it is. So this is a particularly bad thing to have happen to you, because it means that all the questions you ask about that entity are somehow wrong-headed, because you've got its nature wrong. And my favorite example of a category mistake that held back scientific progress is in the decipherment of Egyptian hieroglyphs. So Egyptian hieroglyphs are one of the oldest known writing systems. It's possible that they are the oldest writing system. They go back to at least 3000 BC. And they were used continuously for about 3,500 years. So the last person who could read and write in Egyptian hieroglyphs probably lived somewhere around 500 AD. And it was only deciphered in the 19th century by a Frenchman, Jean-François Champollion. And so for 1,300 years, nobody could read hieroglyphs. All the inscriptions on tombs and on monuments were just silent. Nobody had any understanding of what this script meant. And so the question is, why couldn't we decipher hieroglyphs? And it turns out that when you look at the story, much of the effort for decipherment was based on a fundamental mistake about the nature of the glyph. So there was an assumption that individual glyphs were ideograms, and that means they represent a concept directly. So that was the assumption. They don't depend on any spoken language.
So people still think that hieroglyphics are similar to emojis. So each emoji represents a concept. So they used to think, and people still think, that hieroglyphics, each hieroglyph, whatever glyph, represents a concept.
They just represent a concept directly, kind of like a sign at an airport where it's supposed to be a visual representation of some notion, and it doesn't matter what language you speak, you'll get the idea.
This is 6 years ago. I think they had emojis already at that time.
So that was the assumption, that these were kind of picture writing, and they had to figure out which concept was associated with which symbol to unravel mystery. And it turned out, in fact, that the glyphs represented phonetic values. So things like consonant sounds, vowel sounds, syllable sounds, a completely different sort of thing to be representing. And so all the work that was done under the ideographic assumption, really in the end, it didn't make much sense at all.
So instead, it was like a part of a word. It was a token.
Okay, so I'm going to come back to the story of decipherment later in the talk, but most of this talk is going to be about a different decipherment problem, which is deciphering quantum theory. So there, again, we have this very elaborate formalism, but there isn't agreement about what the quantum formalism says about the nature of reality. So there's lots of different ideas, disagreements among the experts, but no scientific consensus. So for example, you might have heard of some of these ideas. So one interpretation of formalism says that in certain sorts of experiments, cats can go into these strange states of being smeared out between alive and dead states, and it takes a conscious observer to open the box to collapse the cat back into a state of being alive or dead. And whether it's one or the other is completely indeterministic, and nothing in the world fixes which it's going to be. Another view is that actually everything is deterministic, but when you do a quantum measurement, the quantum state of the whole universe branches into 2 parts, and we have parallel worlds, and there's versions of all of us in a parallel world where the quantum measurement came out the other way, and we're all coexisting and evolving deterministically over time. Other approaches to quantum theory involve the notion that if I do a measurement on a particle here, it can happen that it influences the properties of some other particle far away and instantaneously. So this is sometimes called spooky action at a distance. This is also something that people say comes out of the formalism of quantum mechanics. And so the first thing I want to emphasize is that these ideas don't all live in a single interpretation of quantum mechanics. They're really competing ideas for how to make sense of quantum mechanics, or other alternative ideas of how to make sense of the nature of reality given the quantum formalism. I'm going to try to argue that the very fact that we don't have a scientific consensus on the right interpretation of nature of reality given suggests that we haven't got it yet. So like the Sudoku puzzle, when it's complete, you can recognize it's complete. That happens in science as well. When you sort of manage to fit all the constraints of your scientific theory, it usually has the air of truth about it. So for example, when Maxwell, who was thinking about electricity and magnetism, realized that his equations predicted electromagnetic waves that traveled at the speed of light, then he saw that all of optics was actually related to electricity and magnetism, and suddenly the entire theory of optics and the theory of electricity and magnetism mutually supported one another. It was, everything was coherent and fit together, and it was so clearly right. And no scientist to this day has ever seen fit to go back to a time when we thought that optics was not an electromagnetic phenomenon. So the same thing is true here. I think there's some evidence that we haven't got it right simply because none of these pictures are so compelling that they've managed to achieve a scientific consensus that this is the appropriate way of going. So today I'm going to tell you a little bit about my own views about what is the correct direction to take for coming up with the interpretation of quantum theory. And I'm going to try to argue that it's not any of these things. All these various aspects I just told you about are not part of my preferred view. And furthermore, I'm going to try to argue that a lot of the strange features of some of these approaches, the fact that they don't cohere with one another in other physics, is a result of a category mistake. So I want to say that these are all like partially completed Sudoku puzzles where there's some mistake that's been made, and in this case, the mistake has to do with the nature of the quantum state. So the quantum state is really the central theoretical entity in quantum theory. It's usually denoted by the Greek letter psi. You don't need to know too much about what it is, but all the standard interpretations that you hear about all presume that the quantum state is a description of reality. So they presume that as I vary the parameters in the quantum state, I'm describing different universes. And I want to argue that, in fact, the quantum state is a very different sort of entity. It's describing a state of knowledge. So as I vary the parameters in the state, what's varying is they're really describing different statements about the relative likelihoods of various different realities. And you can imagine a variation in the quantum state while reality stays fixed. That variation just corresponds to a variation in our knowledge of reality. So two very different things, like the ideograms and the phonograms, being a state of reality and being a state of knowledge are two different, completely different things. Okay, I want to note that this problem of decipherment, scholars referred to that colloquially before it was deciphered as the riddle of the Sphinx. So I think it's sort of appropriate. There's a lot of analogies between the decipherment of Egyptian hieroglyphs and the problem of interpreting quantum theory. They're both very vexing, difficult problems. So I think it's kind of appropriate to think about the problem of interpreting quantum theory as a sort of modern day version of a quantum flavored version of the riddle of the Sphinx. All right, so let me get started with telling you a little bit about how quantum theory works. So for that, I'm going to consider a simple experiment. So what I have here is a pair of particles that get generated in the middle and taken away to labs. And then there's going to be measurements done on each of these particles. So over here on your left, you've got a measurement device. There's a little pointer. And for simplicity, I'm going to imagine there's only two possible outcomes of this.
This is a general problem in presentations. So he has a pointer, but whoever is editing this video has access to the original PowerPoint, but is not letting us see what he's pointing at. There's no point in showing me his face. I want to see the screen where he's pointing right now. And the editors of the video makers, the video editors of all these videos always miss this one very important point. We never know what he's pointing at. So it's usually impossible to figure out these presentations. Anyway, let's try to figure it out. So I don't know what is S and X. I think maybe X is the direction of measurement, or Y and T and S, I don't know. The probability of X and Y given S and T. So I guess S and T are the directions of measurement. I don't know, maybe X and Y are the results of the measurement. So S and T are the two machines, the left machine and the right machine. X and Y are the results of the measurements.
Measurement, which I'll call 0 and 1. X just labels the outcome. So X takes the value 0 or 1. Similarly, there's a little knob here, and that means you can do different kinds of measurements. But it doesn't really matter what these measurements are. They're measuring two different properties of the system that's coming in. And again, I'll just label those two settings 0 and 1. And I have the same thing over here on the right. I've got these binary outcome measurements with binary settings as well. And so what I can do is I can...
Much better. Okay. So I guess S could be up or down, T could be up or down, the measurement X could be up or down, I mean 0 or 1, Y could be up or down, or 0 or 1. What is the probability of X and Y given S and T? So S and T are both 0, the probability that X equals 0 and Y equals 0 is 0.427. Do these add? This is more than 1. But this 0.4, this might be 1. So given S and T both set to 0, these are the probabilities. S0, T1, these are the probabilities. S is 1, T is 0. So as you can see, X and Y both being 0, I mean, all these are identical. So the only time they change is when S changes. So basically, T has no influence. So as long as S, I mean, during this entire process, it's the same output, identical. It's only when you flipped S, sorry, no. It's only when you flip both S and T to 1. So for every other combination, you are getting the same results. When you flip both S and T to 1, then the results changed significantly, because before x equals 0, y equals 0 was basically 50%, and x equals 1, y equals 1 was basically 50%, and now it changed to x0, y1, and x1, y0 to 50%. So from them being the same, it changed to them being different. Okay.
And set this up, and I can choose a particular pair of settings, like take the case where they're both set to 0, and then I can push the button, generate one of these pairs of particles in a quantum formalism. We describe them by an entangled state. I go off, I do the measurement, and I see what outcome I get. So in the first run, I might get the 0 and the 1 outcome, 0 for x, 1 for y. I do it again, I get.
Why would you use such a complicated, convoluted example? You have to be a genius to figure this out.
The 1, 1 outcome. And I just keep doing it many, many times, and I calculate the relative frequencies of these outcomes. And in the long run, those can be interpreted as the probabilities for these 4 outcomes. And so in this case, for example, with 43% probability, I'm getting both 0. With 43% probability, they're both 1. And with 7% probability each, they're 0, 1, or 1, 0. And I can go through and I can do that for all the other settings. So this is the kind of data you might get out of a quantum experiment. And it's a data table that you can show is predicted by quantum theory for a particular choice of the quantum state here at the center and for particular choices of measurements. This is the kind of thing that quantum theory predicts. And the quantum state appears in the middle of that calculation. So one view is that, well, we'll just interpret the quantum state as a tool you use for calculating these probabilities, which is all you really care about anyhow, and that's it. That's its interpretation. Nothing about the properties of the particles or anything like that. So the first thing I want to do is tell you why I think that sort of approach to the interpretation of quantum state is unsatisfactory. And so for that, I'm going to tell you about a paradox of classical statistics called Simpson's paradox. So the scenario is the following. You have a population of people who have some...
This is genius. This is next level. I mean, he's really destroying. He is completely destroying. I mean, it's not clear. It's not so clear. But this is a complete destruction of big physics. All the physicists, I've never heard anyone dismantle to such an extent. I was with 2 people just before I started streaming. I don't know where they went. I've never heard anyone. I've been listening to a lot of people, but this guy, and he hasn't said anything in the last 4 years. This is from 6 years ago. He has been, I don't know. He decided to keep quiet. I think he said very little. He only has very few lectures.
And you want to test the effectiveness of some drug. So you find the subpopulation of these people who have taken the drug, and you just determine what fraction of them recovered from this illness. So you compute the probability of recovery given that they took the drug. And you look at the subpopulation that didn't take the drug, and you compute what fraction of them recovered. And in this case, it happens that the rate of recovery was greater for those who took the drug. So at this stage, you might say, well, it looks like maybe this drug is effective for this illness. But then you dig a bit deeper, and you look at the men, just the men, and then you notice.
So you notice that the probability of recovering having had taken the drug is greater than the probability of recovery if you didn't take the drug. Okay, it looks like an effective drug. But then you take a look at it and you see that the probability of recovery if you took the drug and you're male is actually smaller than your probability of recovery given that you didn't take the drug and you're male. That's weird. So if you're male, it's not safe and effective.
That when you look at the subpopulation,
You can already tell they're going to strike this video.
of men who didn't take the drug, the rate of recovery is higher than the population of men who took the drug. So it goes the other way relative to the full set.
This has become taboo. You cannot discuss. They've taken down multiple videos where I mentioned these ideas. They don't want anyone to talk about these ideas, about safe and effective anything.
And then the real kicker is that when you look at the women, it goes the other way as well. So for the women as well, the rate of recovery was greater for those who didn't take the drug.
So for women, the probability of recovery, given that you took the drug and you're female, is less than probability of recovery given that you didn't take the drug. So it doesn't look like it's safe and effective when you look at the subpopulations, but when you look at the entire population, it does look like it's safe and effective. So that's weird.
So this really seems like a paradox, because if you try to take a naive interpretation and just say, well, these conditional probabilities should be interpreted as the likelihood you'll recover in each of these various conditions, then it would seem that, if you're a man, you shouldn't take the drug, and if you're a woman, you shouldn't take the drug. But if you're a member of the general population, you should. And that clearly doesn't make any sense at all. So if you haven't seen this paradox...
That's basically quantum mechanics. That's basically Bell's theorem. It's a paradox that needs to be resolved, but obviously it's a paradox. Obviously it doesn't make any sense.
before, let me just persuade you that this can really happen by showing you a data table that achieves exactly these inequalities. So imagine that 300 men took the drug.
Here's an actual example. So 300 men took the drug, 180 recovered, so that's 60%. 100 men did not take the drug, 70 recovered. So the probability of recovery is higher if you did not take the drug, if you're a man. If you're a woman, well, 100 women took the drug, 20% recovered, 300 did not take, 90 recovered, that's 30% recovery with no drug, and 70%, well, 30 compared to 20, 30 is bigger, 70 compared to 60, 70 is bigger. So if you're a male or a woman, you should not take the drug. It's not effective. But this is before the Schmoschmidt. Anyway, but the combined is 3 plus. Oh, we have a visitor. Yes, Stewie, what's up? Can you hear me, Stewie? La 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 la. I cannot hear you. La 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 la. Hey, what's up?
I can't.
What? What's going on?
There.
What?
What's up? Nothing.
What do you want to talk about?
I don't know. Bell's inequality.
Do you know?
BS.
Yeah.
What does that mean?
Do you know anything about quantum mechanics?
Oh, no.
So it's a mathematical inequality. At least we know the audio works. Okay. And here, so if you're a member of the general population, well, out of 400, 200 recovered. So 50% recovery based on taking the drug. While out of 400, right, 400 did not take the drug and 160 recovered, so it's 40%. So obviously, if you're a member of the general population, it's better. You have a high percentage probability of recovering if you take the drug, 50% versus 40%. So you should take the drug. But if you're a male, you shouldn't. If you're a female, you shouldn't. They're gonna strike this video because it's like whatever. Because I'm only talking about males and females. That's not allowed.
That's the denominator here. And 180 of them recovered. You can compute that that's a 60% recovery rate. 100 men did not take the drug. 70 of those recovered. That's a 70% recovery rate. So sure enough, the rate of recovery for those who didn't take the drug is higher than for those who took the drug among the men. For the women, 100 took the drug, 20 recovered. 300 didn't take the drug, 90 of them recovered. So that's a 20% versus a 30% recovery rate. So again, we get the inequality here, which is that for the women, higher recovery rate among those who didn't take the drug. But now we take the total. So if you ask how many people total took the drug, well, 300 men did, 100 women did. That's 400 total. And of them, 200 recovered. So that's a 50% recovery rate. Over here, it's also 400 total who didn't take the drug. But if I add up 79, it's just 160 recovered. So the recovery rate is only 40% in that category. So sure enough, in the combined statistics, the probability of recovery is higher for those who took the drug. So this is very perplexing. And to have a satisfactory resolution of this puzzle, you really need to be able to understand what's going on well enough to answer the question, what should I do? Should I take this drug or not, given this data? So first, I'm going to tell you how to resolve this paradox. First, let me tell you why it feels like a paradox, why we have intuitions that this doesn't make sense. And the reason is that we implicitly think that this is the causal structure. The resolution of the paradox has to do with causal relations among the variables. So we implicitly think that the causal structure must be something like this. So certainly treatment could have a causal influence on recovery.
So this is so incredible. So who recovers? Well, it's based on the treatment and it's based on the gender. You need these two inputs to decide the probability of recovery.
But also gender can have a causal influence on recovery because maybe men are more likely to recover from this illness than women are, regardless of whether they took the drug. And if you think that this is the causal structure, then you really can't get the sorts of statistics that we have here. And the reason is that if this is the causal structure, then the probability of recovery when you take the drug is just the weighted sum of these two probabilities of recovery with the probabilities of being a man or being a woman. And so you would definitely have the inequality going the other way because it would just be the weighted sum of those two inequalities. So you definitely can't get these sorts of statistics if this is the causal structure. And the resolution of the paradox is that this is the causal structure. So it turns out this wasn't a fair drug trial where a coin was flipped to decide whether somebody got the drug or a placebo. It turns out that people got to choose whether they're going to take the drug or not. And if you look at the data, the men preferentially decided to take.
So the reason for this anomaly, this is an anomaly, it's a paradox. What's causing it is because it wasn't a fair trial. They didn't flip a coin who's gonna be taking the medication. They asked for volunteers. So people, the men and the women decided to take the drug. This is very similar to Schmoschmid.
Take the drug, whereas the women preferentially decided to not take the drug. There's 300 men who took the drug, only 100 who didn't, and the opposite for the women. So in that situation,
So
you now have an opportunity for treatment and recovery.
There's more men who took the drug. What did he say? Right, more men took the drug, and with the women, more women did not take the drug. And in general, men, let's see how he resolves it.
To not take the drug. There's 300 men who took the drug, only 100 who didn't, and the opposite for the women. So in that situation, you now have an opportunity for treatment and recovery variables to be correlated, even though treatment does not cause recovery, even though the drug does not cause recovery, because you have a common cause. The gender variable can act as a common cause. So here's what could be going on. It could be that men are more likely to recover from this illness than women are, regardless of whether they take the drug. Men are also more likely to take the drug. And so now you can reason as follows. If I tell you there's a member of the population, they took the drug, what do you think? Are they more likely to have recovered or not? And you
Yeah, but the question is, why did they take the drug?
reason as follows. If they took the drug, they're more likely to have been a man. If they're a man, they're more likely to have recovered. So knowing that somebody took the drug is positive evidence that they recovered, even though the drug doesn't cause recovery. The only reason it's positive evidence is because there's a common cause in the two factors. So you have to disentangle the notions of causation and correlation to get to the bottom of this experiment. And so the answer in this question is that you should not take the drug because this correlation between treatment and recovery is just spurious. It's a result of this common cause, and the drug really isn't effective at all. Okay, so what's the lesson for quantum theory? Well, the lesson is just telling me what the statistics are in one of these experiments is not giving me an understanding of this experiment at the level of what causes what. Like in the Simpsons paradox, when you just gave me the statistics, there was more to be known. I couldn't answer questions like, should I take the drug or not? I needed to have a deeper analysis in terms of what the causal structure was. And so here we can ask, well, what's the causal explanation of why, for example, the variables x and y are correlated for certain values of s and t? Is it just that the particles, so from here on in, I'm going to give the particles a name, they'll be called A and B. Is it that the properties of the particles A and B are correlated because of some common cause, and then when I do measurements of the properties of A and B, those measurement outcomes become correlated because the particles are correlated? That would be one explanation of correlation. Or maybe is it because that, as I choose the setting over on the left, for example, that has a causal influence on the properties of system B. Which setting I chose determines.
Jesus Christ. So particles A and B, A gave us X, B gave us Y, S, right? S and A determine X, but here S also interferes with B. This is already spooky action at a distance.
The properties, and that's part of the reason why the outcomes y are correlated with the outcomes x.
Hello. No.
These are different kinds of causal explanations. The formalism of quantum theory on its own does not tell you what the right picture is. You need an interpretation of that formalism to answer questions like, is this going on or is that going on? So why is it important to have answers to those sorts of questions? Well, one reason is we now know that quantum theory provides advantages for certain applications like computing and cryptography, and we'd like to understand which sorts of tasks quantum computers.
Hello? What's going on?
Can offer an advantage relative to classical computers. But when you're thinking about a quantum circuit or say, a communication protocol or cryptographic protocol, if you don't really understand what causes what and you just have access to the correlation, you're really at a disadvantage. Your intuitions are not solid about what you expect to happen. So if you want to be able to reason about quantum technologies, it's good to have a causal account. And secondly, perhaps more importantly, is that one of the big open problems in physics today is how can we unify quantum theory with our best theory of gravity, which is Einstein's theory of general relativity. And Einstein's theory is about space-time, which can change in response to matter, and that space-time encodes causal relations among events. So it's really a theory about causal structure. So if we can't even answer a simple question about what's going on causally in a very simple experiment on two particles in quantum mechanics, I think it's no wonder that we might have trouble understanding how to unify quantum mechanics with this theory that's all about causal structure. Okay, so it turns out that this question about what's the causal account of what's going on in a quantum experiment is deeply connected to the question of how should we interpret the quantum state as either a state of reality or a state of knowledge. So let me say a few things about the quantum state and that distinction. So it's not going to be important for you to know that much about the mathematical details, but you need to know at least this, that a quantum state is something that's described by a number of real parameters. So if I take the absolute simplest quantum system, which is a two-level quantum system, we call it a qubit, the quantum state has 3 real parameters in it, the sums of their squares are 1, and I can think of it as a point on the surface of a sphere. These numbers would be its coordinates along these axes. But it's important here that this is an abstraction. Don't think of the quantum state as pointing in a direction in physical space. This is just to give you something about what the menu of possibilities for the quantum state are, but keep thinking of it as an abstract thing. The question is really, how should we interpret changes in the values of these parameters? What do changes in these values of these parameters represent? Are they changes in reality, or are they just changes in our knowledge of reality? So that's a bit of a subtle distinction. So let me give you a kind of little thought experiment to try to get clear on what that means. So here's how the thought experiment works. You've moved to Japan, and imagine that you don't read Japanese script. And every day you see this large billboard, the one in blue over here, and it has some numbers on it. You can read the numbers, and you notice that every day the numbers are changing, and you have no idea what it means. But you get in your head after a while that this is probably something to do with the weather. So being a good scientist, you decide, I'm going to figure this out. You're not going to ask anyone what it means. You're just going to figure it out. So every day you take note of what the numbers are. You do some measurements of the properties of the weather. And after a while, you figure out that first number is the temperature on the day in degrees Celsius. And then sometime later, you work out that the second number is the wind speed in kilometers per hour. But even though you try very hard, you don't manage to figure out what the third number represents. You keep measuring more and more properties of the weather, and it seems like none of those properties match the value of that number. And so let's say you do this for 1,000 days, you're stuck, you can't make sense of this. So you try something different. You say, well, what if I look at the collection of days on which that number was, say, 0.5? And then you notice something, that out of that collection of days, and about half of them it rained. And then you look at the collection of days where the number was 0.75, and about 3/4 of them it rained. And you realize what that number represents is the weather forecaster's prediction about the probability of rain on that day. So this number represents nothing about the weather on the day itself, but a fact about what the weather forecaster thought the relative likelihood of two possible states of the weather, whether it's going to rain or not. And that's a very different kind of number. You won't find anything in the properties of the weather on that day that has the value of 0.5. So that's the kind of distinction we're talking about. Do the parameters in the quantum state represent facts about reality? Do their variation correspond to variations in reality? Or should we think of them as representing relative likelihoods to various realities assigned by an agent? All right, well, let's go back to our quantum experiment. I need to tell you a couple of things about how the quantum state appears in the calculation of the correlations that we see in this experiment. So one way you could compute that data table we saw earlier is to use this fact about the quantum formalism, which is if you first take account of the setting you had on the left and the outcome you got, the quantum formalism tells you that if you, say, had a setting at 0 and you got the 0 outcome, that the formalism tells you you should update your description of the quantum state of system B to some particular quantum state. So I'm going to just call it psi 0, 0. And imagine it's represented in this spherical representation as the arrow that points up. And for the other outcome, the x equals 1 outcome, it tells you that it's going to be now represented by this quantum state psi 0, 1, and that corresponds to the arrow that points in the opposite direction on the sphere. If I do a different measurement on that left-hand particle, like that's the s equal to 1 setting, then for each of those outcomes, I get a different pair of quantum states that system B collapses to, which I'll just represent as this arrow pointing right and this arrow pointing left. So this is part of how the formalism of quantum mechanics work. And the question is, what picture of the causal structure of this experiment does this give me for each of the possible interpretations of the quantum state? So let's start with the idea that the quantum state represents reality. So I'm just going to use a very simple model where these four quantum...
This is the superposition as ontological. It's the actual state of the particle.
States I told you about just correspond to 4 different physical states of that B particle. So imagine the B particle has some internal degree of freedom, some internal property, and it can really just be represented as one of 4 possibilities, whatever they are. If you want, you can think of it as a ball that lives inside of one of 4 boxes or something like that. But it's just 4 possibilities. And now imagine that each of these 4 quantum states represents a distinct one of those 4 physical possibilities for particle B. Okay, so that means that when you do a measurement over on the left, with say setting set at 0, and you get the 0 or the 1 outcome, then whatever the physical state of system B was initially, it transitions into one of these 2 physical states, depending on what outcome you got on the left-hand side. So it transitions in this way. And if you instead did setting 1 on the left, right, so you set the knob to 1 instead of 0, then the quantum formalism says if you interpret the quantum states as describing reality, that's going to transition, whatever it started, it's going to transition into one of these other 2 states. So notice that the first pair of states correspond to sort of being in one of the back 2 boxes here. The second pair of states corresponds to being in one of the front 2 boxes. They're mutually exclusive possibilities. And that means that what you choose for the setting over on the left will influence which menu of possibilities B is going to end up in. Is the physical state of B selected from, the menu wherein it's in one of the back 2 boxes, or is it selected from the menu where it's one of the front 2 boxes? You don't get to choose which of these 2 occurs. That's random. You just get an outcome here, which determines which it is. So what you do get to choose is that setting, and that determines whether it's in one of the back or one of the front. And that means that your choice of that knob setting has influenced the physical state of B in a non-trivial way. It can only be in one of these 2 possibilities if it was set at 1, and it can only be in one of the other 2 if it was set at 0. So it means that the setting variable has had a causal influence on the physical state of system B under this interpretation. So this is like the case in the drug trial where the treatment has a causal influence on recovery. Okay, so let me notice something that's a little bit uncomfortable about this approach, which is that Einstein's theory of relativity says that there's a fundamental limit on how fast any causal influence can propagate, and that's the speed of light. And it turns out that I can set up this experiment in a way that the choice of which setting is made here is made at random at the last minute, and this other measurement is done so far away that even after this choice is made, if a signal goes out at the speed of light, it doesn't get here in time before this guy has to report an outcome. And so if this causal influence were propagating at the speed of light, it couldn't change the properties of system B in time before B was subjected to this measurement. And therefore, if I'm going to imagine that this is what's going on, I have to imagine that these causal influences are propagating faster than the speed of light. And that's in tension with Einstein's theory of relativity, and that's why people call this spooky action at a distance. So some people have an idea that maybe this causal influence doesn't even propagate through space-time at all. Maybe it sort of jumps over space-time and immediately has an influence on the other particle far away instantaneously. It's also spooky in another respect, which is that you might have expected that if you've got a causal influence that's running from the left over to the right particle, that you could use that to do things like send messages faster than the speed of light, set up a telephone line that you wouldn't have to wait for light to arrive. But it turns out the quantum formalism says that's not possible, that the statistics of the outcomes here, so the values of y, the different probabilities for the value y, are independent of how you set the knob over on the left. So that's also quite spooky. You've got this causal influence there, and yet you can't use it to send signals. Okay, so that's how you formalism sets the right particle instantaneously. It's also spooky in another respect, which is that you might have expected that if you've got a causal, has people call even after this choice is made, if a signal goes out at the speed of light, it doesn't get here in time before this guy has to report an outcome. And so if this causal influence were propagating at the speed of light, it couldn't change the properties of system B in time before B was subjected to this measurement. And therefore, if I'm going to imagine that this is what's going on, I have to imagine that these causal influences are propagating faster than the speed of light. And that's in tension with Einstein's theory of relativity, and that's why people call this spooky action at a distance. So some people have an idea that maybe this causal influence doesn't even propagate through space-time at all. Maybe it sort of jumps over space-time and immediately has an influence on the other particle far away instantaneously. It's also spooky in another respect, which is that you might have expected that if you've got a causal influence that's running from the left over to the right particle, that you could use that to do things like send messages faster than the speed of light, set up a telephone line that you wouldn't have to wait for light to arrive.
That's so they discovered quantum entanglement. Hey, so you say, okay, let's use it, and the answer is no, you can't use it. So you didn't discover anything. So you don't have anything. How can you say that you have something if you can't use it?
But it turns out the quantum formalism says that's not possible, that the statistics of the outcomes here, so the values of y, the different probabilities for value y, are independent of how you set the knob over on the left. So that's also quite spooky. You've got this causal influence there, and yet you can't use it to send signals. Okay, so that's what happens if you take this view, that quantum states represent reality. Now, what about the other view? What if you take the view that instead they
Now he's going to introduce the epistemic view.
represent just our knowledge of reality? Well, then for these different vectors here, I'm just going to represent them again. I'm going to imagine that this particle B just has 4 physical states, and these 4 quantum states are represented by a distribution, a probability distribution, now where I say, well, I know it's not in one of the front 2 boxes, and it's equally likely to be in one of the back 2 boxes. And for this one, I'll interpret it as being equally likely to be in one of the front 2 boxes, but definitely not in one of the back 2 boxes. And for these 2, it's definitely on the left, definitely on the right, but we don't know whether it's in the front or the back. So say you take that view, then you interpret the same experiment in a very different way. You say, well, my choice of what to measure over here, and I can choose the setting 0, get outcomes 0, 1. That just determines how I update my beliefs about the particle B. So I update, whatever I believed about particle B initially. Maybe I had no information about what physical state was. I'm going to update my beliefs to being it's definitely in one of the back options if the outcome was 0, and it's definitely one of the front options if the outcome was 1. But if I'm doing the other setting, the 1 setting, then I update my beliefs differently. I update to one of the left options or one of the right options depending on the outcome. So all that's happening as I register the outcome over here is I'm learning how I'm going to refine my knowledge. Am I going to learn about this?
So S equals 0. What is S equals 0? What?
Causal influence there, and yet you can't use it to send signals. Okay, so that's what happens if you take this view, that quantum states represent reality. Now, what about the other view? What if you take the view that instead they represent just our knowledge of reality? Well, then for these different vectors here, I'm just going to represent them again. I'm going to imagine that this particle B just has 4 physical states, and these 4 quantum states are represented by a distribution, a probability distribution, now where I say, well, I know it's not in one of the front 2 boxes, and it's equally likely to be in one of the back 2 boxes. And for this one, I'll interpret it as being equally likely to be in one of the front 2 boxes, but definitely not in one of the back 2 boxes. And for these 2, it's definitely on the left, definitely on the right, but we don't know whether it's in the front or the back. So say you take that view, then you interpret the same experiment in a very different way. You say, well, my choice of what to measure over here, and I can choose the setting 0, get outcomes 0, 1. That just determines how I update my beliefs about the particle B. So I update, whatever I believed about particle B initially. Maybe I
Let's check my schedule.
had no information about what physical state was. I'm going to update my beliefs to being it's definitely in one of the back options if the outcome was 0, and it's definitely one of the front options if the outcome was 1. But if I'm doing the other setting, the 1 setting, then I update my beliefs differently. I update to one of the left options or one of the right options depending on the outcome. So all that's happening as I register the outcome. Over here is I'm learning how I'm going to refine my knowledge. Am I going to learn about this back front degree of freedom, or am I going to learn about this right left degree of freedom? I get to choose which sorts of properties of A I'm going to learn about.
Okay, so S equals 0
Properties of A are correlated with properties of
is forward and back. X equals 0, X equals 1, and S equals 1 is left and right X. Okay.
B. So what I measure on A will determine what I can learn about B. And here I'm just learning 2 different kinds of properties about B, depending on what setting I chose. But all along, system B can be in some fixed physical state. So maybe it's, for example, in the back left-hand corner. And then if that's the case, then if I choose to measure the 0 setting, I'll get the 0 outcome. And I'll refine my information from knowing nothing about where it is to knowing that it's in one of the back 2. Or if I choose to measure the other possibility, I'll refine my information from knowing nothing to knowing it's one of the left ones. But all along, it's just been in that back corner, and nothing I've chosen over on the left is influencing or changing its physical state. Its physical state is staying the same. All that's changing is my description of what I know about that physical state. What are the options that seem possible relative to what I've learned? Okay. So in this case, this is clearly like the drug trial where the treatment simply informs you about the recovery variable by virtue of some common cause acting on the 2. So here, the properties of A and B are correlated by virtue of common cause. And the reason learning X teaches me something about B and Y is because of that common cause. But there's no influence. Good. This experiment I've just told you about was actually proposed by Einstein in a very famous paper that he co-authored with Podolsky and Rosen. And the point of that paper was that Einstein wanted to point out that if you take the view that the quantum state describes reality, then you're forced to this uncomfortable conclusion that there's going to be these spooky action at a distance. He coined that term. And it was basically a criticism of that idea. He thought, this is inconsistent with the principle of relativity, and therefore we should dismiss this idea. And the paper itself wasn't written by Einstein. Scholars think it was written by Podolsky. And if you read Einstein's correspondence from that period, he actually confides to his correspondence that he didn't quite like the way the paper turned out. And he said, look, the main point I was trying to make was kind of lost, so let me make it for you. And
This is incredible. Because I'm arguing with people about what EPR should have said, and they all say, no, EPR doesn't say that. And Einstein has said, yeah, that's not what I want. It didn't come out right. Let me explain to you what I really meant. What he really meant is what I keep arguing with people.
And so if you read that correspondence, you'll see that the point he was really trying to make was that the quantum state should be interpreted as a state of
So Psi 2 does not describe the totality of what really pertains to the partial system 2. Rather only, so 2 is the right, we have two systems, 1 and 2. We have two entangled particles, 1 and 2. So Psi 2 does not describe the totality of what really pertains to the partial system 2, rather only to what we know about it in this particular case. This is exactly my point, that superposition is epistemic. It's not ontologic according to Einstein, obviously. I'm inclined to the opinion that the wave function does not completely describe what is real, but only maximal knowledge regarding that which really exists. So the wave function is just our knowledge.
knowledge. So here's a quote from one of his papers. So he says, Psi 2, that's what we would call the quantum state of system B. Psi 2 does not...
From one of his papers, or one of the correspondences.
...is that the quantum state should be interpreted as a state of knowledge. So here's a quote from one of his papers. So he says, Psi 2, that's what we would call the quantum state of system B.
And this minimizes the importance of quantum mechanics. This turns the weirdness of quantum mechanics to just our lack of knowledge. It's really no big deal. I mean, the fact that physicists have turned this into this weirdness in the universe is bizarre.
Psi 2 does not describe the totality...
Since when something is weird, you say the universe is weird. Usually when something is weird, you say, my understanding is incomplete.
...of what really pertains to the partial system 2.
Obviously. If I see a phenomenon and I cannot explain it, I don't argue that the universe is unexplainable inherently. That's ridiculous. I don't know exactly why it rains. I don't know. So is the universe unknowable because of that? But that's a weird conclusion.
Rather only what we know about it in this particular case. In another letter, he writes, I incline to the opinion that the wave function, which is another way of saying the quantum state, does not completely describe what is real, but only maximal knowledge regarding that which really exists. Okay, so
he has another screen in front of him in the audience. This is really good.
It's very clearly this notion that maybe the quantum state is just describing what we know. So that was 1935. And since then...
This is incredible. It's like his message was completely lost to history. No one today believes this. This is incredible that I had to rediscover this on my own.
And I would say there's been a lot of progress on...
All I knew is that Einstein didn't like quantum mechanics. And from this, I came to the exact conclusion that he came to. On my own.
Yeah, the question of whether we can really make sense of quantum theory in this way as a state of knowledge. So I'm not going to tell you about the whole history of that project, but let me just mention one thing. We now know that there are certain parts of quantum theory where we really can interpret the entire formalism in a way where quantum states really are just conventional states of knowledge, meaning probability distributions over some set of physical states, exactly the kind of way I showed you. So I'm calling these the Clifford fragments of quantum theory. So the idea is that quantum theory allows for a given type of system all sorts of different preparations you could do on it, all sorts of different measurements you could do on it, transformations, and these fragments just look at a subset of those. They say consider only a subset of the states and a subset of the measurements and the transformations. And it's still a very rich theory because I can compose that subset in any way I like, but I never get out of that subset. But the interesting thing is that although they're in some sense a small part of quantum theory, they already contain all the sorts of mysterious quantum phenomena that you might have heard of, like entangled states, this remote collapse of the wave function we've just been talking about, this idea of a superposition principle, interference phenomena, teleportation, something called the no-cloning theorem, wave-particle duality, and the list goes on.
I mean, obviously, these are just states of our knowledge. I mean, this is so ridiculous that all the greatest minds of our generation have bought into this interpretation that this is the nature of reality, and they all just argue about what interpretation of reality. But they all agree that reality, it's either some collapse of a wave function, it really collapses, or the multiverse. I mean, they all believe the cat is both dead and alive.
On and on. They're all in there in those kinds of theories. And so the fact that in those kinds of theories we can clearly interpret the quantum state.
I mean, if the audience, if they live the nuisance that quantum mechanics is to me, they should be sitting there in awe. They should be picking up their jaws from the floor at this point. It's like, where have you been? Why do we not hear more people like you? 193 comments. My comment: big physics is not going to like this interpretation of quantum mechanics and entanglement. Let's see how much they hate him. Oh my god. Oh my god. Try to find a flaw in Bell experiment first. The rest is not a science. So this guy Evgeny. So he says what they all say. You have to resolve the paradox. It's like, I don't have to resolve the paradox. There's been plenty. This is God of the gaps. I'm not gonna waste my life to resolve every paradox you parasites come up with every day of the week. You can come up with infinite paradoxes. I'm not gonna sit at home and just solve your paradoxes. So that's what he says. No, you have to resolve Bell's paradox. I don't have to resolve anything. It's a 5.6 discrepancy that we cannot account for in the accounting. That's not a reason to get rid of logic itself. So therefore we can get rid of logic. What an idiot. He's not a good presenter. I don't think. Oh my god. Exactly. It's just not understood. Exactly. Exactly. I mean, you guys don't have an understanding of reality. You cannot explain to me, I haven't heard a good explanation about quantum quantum particles, the double slit experiment. Give me a complete um, description of the double slit experiment. Go ahead, I'm listening. Oh, you don't have one? Well, so what's the point? So what's the point in having paradoxes? There's just one more paradox. It's incomplete. We don't have a complete picture yet. So of course you're going to come up with contradictions. Of course you're going to invent contradictions. This is so deep. What this guy is saying is so deep. This is so deep. This explains so much. He says, look, everybody agrees quantum mechanics is incomplete. The fact that you have Bell's theorem, that's just another piece of evidence that we don't completely understand quantum mechanics. So you can come up, of course you're going to come up with many paradoxes. I mean, the very collapse of the wave function. Where Schrodinger doesn't have a collapse of the wave function. Where in Schrodinger does the wave function collapse? The wave function doesn't collapse. You had to invent the collapse in order to match the, the experiments. Where in the experiments, right? And that's why you have the Everett multiverse, because there's no wave function collapse. So So yeah, you can come up with as many paradoxes as you want, as long as we don't understand quantum mechanics. So of course you're going to have actual paradoxes because we don't understand it. How do you know what will help, what will not help? Only new experiments in math would help. How do you know? And what if quantum theory cannot be represented by any version of the classical picture of physics and cannot be understood by using little balls, waves, springs, and so on? Would it be a category mistake? I don't know about the category mistake. Like I think that's an overkill, what he said. But the fact is, we don't understand. And we shouldn't give up. I mean, the way physicists behave is as if we're never going to understand anything. And therefore the universe cannot be understood, and therefore it is the intrinsic nature of the universe that it cannot be understood, which is absolute bonkers. Why would you say that? So this is so what do you call it when somebody gives up? What do you call it when somebody always gives up? Oh my god, what's the word for that? Defeatist. This is such a defeatist attitude, such a loser attitude. I mean, who are these losers? What absolute losers! This is so befitting the mindset of someone who goes into academia, someone who becomes an academician, someone who such a loser, such a lowlife. I don't understand it. Therefore, the universe, the nature of the universe is it cannot be understood. Give me money. Give me my salary. I don't want to work hard. Like, no, you're not going to get your salary until you figure it out. You're getting paid to figure things out. Go home, no salary, quit your job, come back when you have an answer. There have been thousands. It's always the best idea to go to the very last comments. I mean, the very first comments, chronologically speaking. This is the kind of lecture you sincerely don't watch. After 20 minutes, and I find myself not even understanding what the lecture is really supposed to be about. The level of people who get a chance to give a lecture is way too high compared to the level of people who can actually explain the given material properly. Choose more carefully next time. Are you out of your mind? This lecture is really not complicated. I usually complain. That's usually my complaint. That is usually my line. But this guy is actually very simplifying quantum mechanics. I would have left after 10 minutes before I went crazy. 15 uhs in 3 sentences and you lose credibility. These people are insane. A lot of bad dudes in the audience. Nice. What are you bald? Oh, this is very old idea. What are you talking about? Show me. What's your reference? What is your reference? How do you spell reference? Reference? All the old people in the audience. Everyone is confused. No! Dr. Speakins might be a good scientist, but I think not so good teacher unless the audience consists of physics professors. He's the first one to actually simplify quantum mechanics, and this is how. Wait, what just?
Hello, can you hear me,
Hi,
Mr. Slade?
hi. Who are you?
I don't know you. Might just joined this voice call.
Wait, I asked like, what should I call you, Mr. Dot?
I just told you I joined this voice call. I didn't know anybody.
But what's your name? What should I call you? What should I? How should I? How can I reference you when I talk to you?
I'm sorry, it's personal. I can't give you my
No,
Discord.
you say it says Dot. Just should I call you Dot?
Oh, call me Saitama.
Okay, Saitama. All right, Saitama. So, do you know quantum do you know Bell's inequality?
Uh,
Yeah. Can you hear
I know.
me?
Why you assuming that I don't know that?
What?
Stupid or something? Why are you asking this question?
If you know Bell's inequality?
I know that. Of course I know what it is, buddy.
Oh, so can you explain to me Bell's inequality?
You don't know it?
No, not really. A little bit.
Oh, yeah, it's about like when electrons are sent across the magnetic.
Electrons are sent across the magnetic, yeah.
Yeah. Did you get it right? Did you understand what I mean by that?
I mean that you're referring to. I mean, Bell's inequality. I guess you could do it with electrons. You can do it with photons. You could do it with photons. I think with You can filter them by spin. What do you call it? Forgot the name.
Wait,
Yeah.
wait. Listen, buddy. Listen. You're the one asking me what that is. I know what that is. You don't know what that is. You're the one who asked me, okay? So I'm trying to teach you what that. I'm trying to teach you, okay?
I'm listening. Go ahead. Explain to me
I already told you.
Bell's inequality is when you send electrons through a magnetic. Hello?
Yeah, I already told you that. What is your problem, dude? You trying to make fun of me or something?
No, I'm trying to understand. Why are you getting upset? Look, you don't have to stay here. You don't have to talk to me if you don't like me or whatever. So it's up to you.
No, but listen, you have the voice called Shannon Lane,
Yeah.
Barson Equality. And you don't even know, you don't even know what that is. Like, why? I don't understand.
Okay. So what do you want to do? You how can I help you?
I just want to talk. I don't have a debate with you.
Go ahead. I would like to debate Bell's inequality.
Yeah, what do you want to talk about, buddy?
Bell's inequality.
Right, you can go first. What kind of question? What do you want? What kind of question?
Well,
What kind of question do you have?
can you explain it?
I already explained it once. I'm not gonna explain it again. All right?
Okay. Have a great rest of your day.
Okay, well, I don't care.
So let me know if you want to have a discussion. If you don't want to have a discussion, that's fine. I'm gonna watch a
Yeah.
YouTube video.
Is the state of knowledge means that all these kinds of
Right.
phenomena can
Right.
be understood.
You buy that. Leave.
What do you mean leave? It's my room. I'm waiting to debate people. You don't want to debate, so goodbye. I don't want to bother you.
I already told you I want to debate, but you keep telling me to fucking repeat stuff. I don't want to repeat anything,
Then
buddy.
goodbye. Then if you don't want to repeat, then leave. What do you want me to do? You want
Yeah, then.
hmm?
Yeah, I just wanna listen. I don't know.
I don't know what it means to listen. I honestly don't know what it means to listen. You wanna have a discussion, so let's have a discussion. But in a discussion, you have to answer questions, and if you have to repeat, you have to repeat. So you don't need to get upset that you have to repeat. So,
Okay.
okay.
Okay. I'm gonna be honest with you. Okay. I'm gonna be honest with you.
Hmm.
I don't know what that means. I don't know what that means. I just search it up on Google.
Oh, okay. Yeah, I'm. Look, Bell's inequality. I'll tell you what I know. So Bell's inequality says that there is a contradiction between what we expect in a certain in Bell's experiment. There's something called Bell's test, which I'll explain to you in a second. So Bell's test, we expect a specific result for Bell's test, but when we run the test, we don't get that result.
Okay.
So there's a
Yeah.
so there seems to be a contradiction between what we expect and what we get. That's it. Now, Bell's test, it's a little complicated. It's so you can take two electrons, for example, that are entangled. That
Okay.
that means when you created them, so in the beginning you had a particle and it decayed into two particles. Let's say into an electron and a positron, which a positron is just a positive electron. So it could happen. Sometimes it happens even with a gamma particle. So you could start with a gamma particle, which is basically a photon, and it could turn into an electron positron pair. It could decay or it could turn into an electron positron pair.
Okay.
Okay, so but the original gamma particle, the photon, didn't have any spin. It did not spin, whatever that means. But when it turned into an electron positron pair, then electrons and positrons, they spin. They have spin. An electron always spins, and a positron always spins. So when the photon turned into an electron positron pair, so the spins of the electron and the positron must be in opposite directions in order for angular momentum to be conserved. So since the photon did not spin, therefore the electron and the positron must have opposite spin. Are you following so far?
Yeah, but it feels like you're trying to act smart, you know, you're trying to like have more authority than me, and you're trying to like,
No, no,
I'm
no.
not stupid, right? You're trying
No,
to give me advice like that.
no. Here, I'll give you a link to a video that you can watch, and this is exactly what he's going to explain. Let me give you a link. It's called the Science Asylum Entanglement. Let me see if I can find it. Yeah, this is it.
Immediate surroundings.
Wait, what are you gonna do? Trying to send me a link or?
Yeah, I'm gonna send you a link in a second.
Yeah, but I'm not gonna click on that link because I know you're trying to grab my IP address.
You can go to YouTube and search for the video. I'll give you the name of the video.
I'm not gonna search for anything. Trying to get my IP address. I'm not stupid, all right?
I'm gonna give you a screenshot of my laptop so you can do whatever you want with the screenshot. If you don't trust me, you can search for this.
Huh? I know. I'm not stupid. I know there's stuff like that. There's like phishing links for IP address and the
Just
and the.
search. You can search Google for what I show you. Quantum entanglement explained. The Science Asylum. I'll show you what I searched for. This is literally what I searched for. You can Google it.
Okay.
And
But I have a question. What does that like? What does that do to you? I mean, what do you gain from that? Like from this stuff?
what do I gain from understanding Bell's inequality, from debating and discussing Bell's inequality?
Yeah, what do you gain from that?
So the smartest people in the world, they believe in Bell's inequality, and I think they're all wrong. And I think that quantum computing, therefore, does not exist.
Do you believe in God?
No, I don't believe in God.
Why not?
There's no evidence. This universe looks exactly as it would if there is no God. This universe.
Well,
Go ahead.
well, I'm agnostic. I I don't believe in any religion, but I believe there is a God, of course.
hmm So then you must be very young. Are you
I'm not
18?
young. I'm 19. I'm 19. I'm 19 years old.
Yeah, you're very young. So when you're my age, you'll realize that it's God is obviously there is no God. It's going to take you some time. When I was your age, I also believed in fairy tales. It's a fairy tale.
Wait. Give me 1 minute to trying to. I'm not trying to be rude to you. You seem like a nice guy, but you're talking to me like I'm a dumb person. You like have authority over me. You don't have authority over me, buddy. Okay.
What?
It feels like you're trying to like act smart and you're trying to like make me sound stupid because you're older than me. You're trying to have more authority than me. You don't have more authority than me. Okay.
Okay. I I'm not interested in authority. I'm not an authoritative person. My name is Mr. Slave. Obviously, I'm not into being authoritative.
Okay. How old are you? How old are you?
I'm very old, very old.
You don't sound old. You sound like you're maybe 23 years old.
No, I'm very old. My voice is young, but I'm a very old man.
Can you tell me your age?
No, no, I don't. I try not to disclose any information in general.
Well, what do you for a living? Like, how do you get money?
Um, I I just have money. I'm an old man. Old men usually have money.
Okay. All right.
Yeah, when I was your age, I didn't have a penny, and now I have a lot of money.
All right. Why are you bragging about your money? I don't care. I'm just asking you stuff. It's like you don't need to
I'm
brag
not
about your money. Come on.
I'm not bragging. What do you mean bragging? How am I bragging? I'm not bragging. I didn't I didn't tell you that it's some accomplishment. I didn't accomplish it.
Yeah, just because you have money doesn't mean like you're a better person. Money
No,
doesn't buy you.
of course not. Of course not. My life is normal. I mean, my life is comfortable, but I don't mean
Okay.
to make you feel to get you upset. That's not my intention. So you support Putin?
Uh, no, he's a mass killer, genocide killer.
Wait, so do you support him or not?
No, I don't like him. He's a killer.
Okay. Are you Polish?
He's a personal information. I'm not gonna give you that, right? I know you're trying to get my IP address by sending me the link. Now you're trying to get my IP address by asking me where I'm from.
Oh my God. I don't believe you're serious. I think you're joking, right?
I'm not joking. I mean, why would you send a link in Discord? Discord isn't a safe place to send links in. I would have never opened
Oh
this
my
link
God.
anyway.
It's I sent you text. The last thing I sent you is text. You don't like
Right.
you think I'm going to use the text to get your IP address somehow?
I don't know. It's maybe your video. I don't know.
No. No. I mean, you could argue that a link could do some damage. An image, probably not. Maybe. I mean, it would. I mean, I don't know how. How would an image? Because I don't think you're not using an iPhone. You're probably using an Android. If you're so worried about your privacy, the first thing you should do is ditch the Android, switch to iPhone. But
No,
yeah,
our iPhone have lower security than the Android.
no, I don't think so. I don't think so. Anyway, but if you search YouTube, just search for the words "the science asylum and entanglement." Hello, Nibble. If you search,
Hey.
hey, Nibble, do you know Bell's inequality? Do you know quantum mechanics?
No, I was just seeing what the topic of the room was. I don't know much about that.
Quantum mechanics? Do you know physics?
Yeah, I know physics. I know what quantum mechanics is, but I don't know what Bell's inequality is.
Wait, Nibble. If you don't know what that is, why will you join? This is a topic for this. We're gonna talk about this right now. You shouldn't join if you don't know if you don't know it.
I'm just
No.
hopping around, man.
No. Nibble, you're welcome to
Carry on.
stay. Yeah, Nibble, you're welcome to stay. No, Nibble, you should unmute yourself. I want to talk to you.
Okay.
Yeah, because the conversation with Mr. Dot is it's not going anywhere. He um I forgot how he wanted me to reference him. Saitama. Hello, Genma.
Hi.
Do you know quantum mechanics?
Not really. I'm not really good at physics.
Why did you join though? Why did you join? Why did you join?
Okay, Saitama, stop it.
Why did you join?
Why do you keep asking why did they join? Anyway, I'm trying to debate quantum mechanics, quantum entanglement.
Okay, I didn't knew what Bose and inequality
It has.
is, so I didn't even knew that it
Can
has
you,
to do
Genma?
something with quantum
Genma,
mechanics. Yeah.
Genma, your audio is very low. Can you raise your mic somehow?
Sure.
Anyway, so you know the story about the cat, Schrodinger's cat? Have you ever heard of Schrodinger's cat?
Yeah, I know it. I know this. Yes.
Okay, so the question uh, is the cat both dead and alive, or is the cat dead or alive? What do you believe? Do you want me to repeat? Go ahead.
Okay, so dead or alive or dead and alive, right?
Yes.
I think, like I already said, I don't know much about quantum mechanics, but I guess dead or alive. This makes more sense to me. But I know that that's a paradox, right? So
I don't think it's a paradox. I think it's a question. Like when you're not looking at the moon, is the moon still there? Or does the moon
Oh.
only come into existence when you look at it? When you
yeah, I think it's a philosophical question, isn't it?
I don't know.
Like,
What do you think? Mm-hmm.
I think like I had this discussion a few days ago
Mm-hmm.
where I was discussing if nobody notices that the tree is falling down and it makes a sound, and nobody noticed it. Did the tree make a sound? And in my opinion, like, yeah, it depends on what premises do you have, like what definition you have. But Yes, I would say that nobody needs to see it or to sense it or in any way to experience it to make it happen. So I guess she's dead or alive.
Okay, but how can we prove? How can we prove if the cat is, if the moon is there when we're not looking, if the cat is there when we're not looking, if the cat is dead and alive, dead or alive? How can we prove it?
I guess we can't.
I think we can because we have cell phones. We have cell phones. We can record everything. We can record everything with our cell phones.
But
But
when
let's
you
say,
record it with us,
but let's
yeah,
say
okay,
you,
do it.
but let's say you didn't record it. Let's say you're not. The point is you're not looking. Everybody agrees that if you're looking, then the cat is dead or alive. The question is, when you're not looking, is the cat dead or alive, or is it dead and alive?
Well, it depends. If you saw the cat alive, then you have to assume it's still alive. If you saw it dead, you have to assume it's still dead.
Yes, but as long as you're not looking, what is the state of the cat? When you're not
This,
looking, before you look, after you look, everybody agrees it's either dead or alive. But before you look, if you have to, I mean, what's your opinion? Is it dead and alive or dead or alive before you look?
before you look, is he's dead and alive then.
So so you think that it's dead and alive, meaning it's in a state that we've never seen before. It's in a, this is what they call a superposition. So you think the cat is in a superposition of being both dead and alive when we're not looking.
The thing, there is no answer for that until you see the shape of the cat. This is how it is.
But the question is,
Can
everybody agrees that we don't know. But the question is, what is the reality? As long as we don't know, what is the reality? Is the reality one of the above, or is it a mixture of the two? When we don't
the
know,
reality is one of them.
so how do you know? How do you know that that is the answer? That the reality is one of them? Maybe the reality is both of them. How do you know?
Because this is how it is proven. This is how the world works. This is how everything works. You
But
have
how
to
do
be
you
dead or alive.
but how do you know? How do you know that this is how the world works? Maybe the world works different than what you say, because no one has ever seen, right? We're talking about the state when we don't know. The moon when we're not looking. How do we know that it's there?
Because there is someone else looking at the same time when you're not looking.
Fine. If somebody's looking, then that's fine. But if nobody's looking, as long as you're not looking, how do you know that the moon is there? Maybe the moon is not there. How do you know?
Well, listen, buddy, I think these questions are just, I mean, even though you know the answer for this question, it doesn't make any sense anyways. I mean, what is the point of those questions? Just nonsense, you know.
Well, this is, it's a very big discussion. This is the greatest disagreement in the history of all of physics. This is what Bell's theorem is basically all about. This is the this is the notion. I mean, this is what Schrodinger's cat is about. This is a very, I understand that you don't like the question, but if you talk to physicists, most physicists would tell you that it's a very important question, and the answer would surprise you, what they would say. But if you don't like this discussion, you don't have to stay.
I'm just telling you, I'm trying to learn new stuff. But physics, like, I don't believe in them. Science, I believe they're just like, I think they satanic and they believe in the devil. I don't believe in those people.
Oh my God. Oh my God. No, no. They're not satanic. What are you talking about, satanic? There's no Satan. Satan doesn't exist. There's no God. Stop it with your nonsense. The question is, how do we know if the moon is there or not when we're not looking? Can we prove it one way or the other?
You can't. There's no way. What are you talking about? You cannot do that.
So Einstein came up.
I mean,
Mhm.
I guess you can. Like, if you're allowed to use other senses than just your vision, and if you
No,
can, like, for an example, I don't know, make some tests and stuff like this, like with
right.
right, like it's if whereas obviously it's possible to prove something that we don't see. Like that's not, but I think that's not the point, right?
Actually, it's close to the point. So
Okay.
Einstein came up. This was a big disagreement, and in 1935, Einstein wrote a very famous paper that he offered how to resolve this question. This question is very important when it comes to quantum mechanics. This is at the very foundation of quantum mechanics. So nobody understands quantum mechanics. Quantum mechanics gives you a big headache when you try to understand it.
Okay.
Anyway, so Einstein came up with the following idea. He said, it's really complicated, but he said that we can use something called entanglement in order to figure it out. So he said you can create, it's possible to create two particles that have opposite spins. Anyway, this becomes very complicated very quickly. I put a link in the side chat to a video. Maybe maybe we should watch it.
Hey, crazies. Experience with physics has taught us that the universe is inherently local. Each point in space can only affect its immediate surroundings. So, influence at a distance must propagate through the intervening space. And that process is always limited by the speed of light. Or is it? Quantum entanglement might have something to say about this. Lab for World Quantum Day. But more on that later. Where do I begin? Everyone loves a good thought experiment. Imagine there's a high energy photon. It's just minding its own business, traveling along. Then suddenly an atomic nucleus jumps out in front of it. The nerve of some nuclei. Anyway, the interaction transforms the photon into an electron-positron pair. So it collided with the nucleus and broke apart? Well, no, at least not in the way you're probably thinking. This isn't like two objects being smashed together or something. Particles never really touch. Plus, it's not like this photon is made of an electron and a positron. They're not inside there. The photon just ceases to exist, and some of its properties are given to the new particles. Of course, energy must be conserved. Conservation of energy shall not be violated! Linear and angular momentum are also conserved, and the atomic nucleus helps with that. Yes, this particle pair, this electron and positron, are antiparticles, but there's so much more than that. They're entangled particles. Their properties are linked. We know they must be opposite. If the electron is oriented up, the positron must be oriented down. If the electron is oriented down, the positron must be oriented up. They share a single state. It doesn't make sense to talk about them separately. But this is quantum mechanics, so those two states are not the only ones available. Say we don't know how either of them is oriented. The property is in what we call a superposition. Both particles are showing an essence of upness and downness at the same time. Because, quantum particles can do that. They're still entangled though, so their states are still opposite. It's just unclear which of the base states we'll find when we measure them. If you want more details, I have a video on superposition you can check out later. In case you need better nonsense. Available at the Science Asylum store. But there's really only one more thing you need to understand right now. Superpositions are not measurable. We can only create devices that we intuitively understand, and measured particles will always be in states that those devices measure. This random particle's orientation may be in a superposition, but that all changes when it encounters one of our devices. If the device measures up and down, we'll find that the particle is either oriented up or down, not in a superposition. If the device measures left and right, we'll find the particle is oriented left or right, not in a superposition. The interaction with the device changes the particle, or at least it changes what we can know about the particle. And before you ask, this has nothing to do with the person taking the measurement. Quantum mechanics is not magic. It's about the information that's available, not the information we have. So now that we have entangled particles in a superposition, let's separate them. And I mean separate them, like a lot. We'll put them so far apart that it would even take light a noticeable amount of time to travel between them. The Earth-Moon distance ought to do nicely. That's a minimum one-way trip of 1.3 seconds. Next, we break the universe. I measure the electron here on Earth and find that it's oriented up. In that case, I immediately know that the positron on the moon is oriented down. If astronaut clone measures his positron, it must be oriented down. The superposition has collapsed into this state. How does that break the universe? How did the positron know to be oriented down? But it was in that state the whole time, wasn't it? We just didn't know, right? Well, that's certainly what a whole group of physicists thought back in the day. To the timeline. Quantum mechanics was born in the 1920s, almost a century ago. The de Broglie wave hypothesis, Schrodinger's equation, the Heisenberg uncertainty principle, all published in the 1920s, and all suggesting that the universe is inherently probabilistic. It was a philosophy championed by Niels Bohr. But then in 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a joint paper where they outlined a thought experiment a lot like the one we just described. This paper was designed to settle a debate. Do superpositions physically exist? Can a particle really be in a state that shows an essence of upness and downness? If that's true, then my measured electron had to communicate with the positron on the moon instantaneously. Just in case astronaut clone decided to measure his positron at the same time. It didn't have the luxury of waiting the 1.3 seconds it takes light to get there. Then again, maybe quantum mechanics is just a statement of our ignorance. Maybe there are hidden variables at play. The particles could have definite states the whole time. We just didn't know what they were. This thought experiment, now known as the EPR paradox, doesn't truly answer this question. It certainly shows how counterintuitive superpositions are, but counterintuitive doesn't mean wrong. Einstein was involved in the
inequality. And why is it BS?
Do you know quantum mechanics?
Oh, it's actual fucking quantum physics. Never mind. Good luck. Sorry.
invention of modern relativity. He should have known better. Anyway, the debate wouldn't be settled until 1964 by John Stuart Bell, who proposed a revised experiment. It turns out that everyone was so focused on measuring up and down and left and right that no one thought to measure along a diagonal. For intelligent beings, humans can get some serious tunnel vision. Anyway, let's redesign our detectors a bit. Each of the two detectors is capable of taking a measurement along 3 different directions. It doesn't matter which 3 directions, as long as there are 3 different directions, and the detectors are designed identically. For simplicity, we'll make them all 120 degrees apart. Which of the three directions is being tested will be selected at random for each particle, and the two detectors are changed independently of each other. Next, let's label the outward orientation to be positive for each of the three directions, which makes all the inward orientations negative by default. Then we do this experiment a crap ton of times. The question is, how often do these particles have opposite signs? If the two detectors happen to be measuring the same direction, we'll get what we expect. Two entangled particles with opposite orientations, opposite signs. But something interesting happens when the two detectors aren't measuring the same direction. If they're not, then there's no requirement the signs be opposite. They could be the same. How often we expect those cases to have opposite signs depends on our philosophy. So this experiment can test if there are hidden variables. Assuming the superposition isn't physical and the particles had a definite state the entire time, there are only 6 possible outcomes. So all we have to do is count. If the detectors measure the same direction,
What is positive A, positive B, negative C, negative A, negative B, positive C? What is that? What is ABC? What is positive and negative? Positive?
I don't know. I never seen stuff like that.
I mean, positive and negative, he said that's the direction. What is ABC? Oh, the ABC. Okay, so that's ABC. So the positive A is going that way, positive C, and why is B on the left? All right, so it's ABC, fine. Okay. So positive A, I mean, the electron could be positive A. I don't understand what it says here. So the electron could be could be positive A or negative A, positive B or negative B. Well, it depends on how we measure. So we might measure the electron in A, B, or C direction and the positron A, B, C directions. Okay. He doesn't explain this.
possible outcomes. So all we have to do is count. If the detectors measure the same direction, the particles always have opposite orientations.
Okay. So if they measure the same direction, meaning A and A, then it's always opposite directions. So positive A, negative A, positive A, negative A, negative A, positive A, negative A, positive A, negative A, positive A. All right. That's if they have opposite directions. And the same for B. So positive B, negative B, negative B, positive B, negative B, positive B, positive B, negative B, negative B, positive B, positive B, negative B. And the same for C. Negative C, positive C, positive C, negative, negative, positive, negative, positive, positive, negative, positive. Okay, so that's if they're the same direction. But what if they're not the same direction? So what do we expect? What do we expect? Let's say we're measuring positive A. What do we expect the positron to do if we're measuring it at B? Do we expect... I don't know what we're expecting. Anyway, but he said, okay, let's count.
I think it will be without the.
It will
It will be without the minus or plus.
No, it's not. The minus and the minus and plus are the answers. The B is the direction. So you have to have a. I mean, we're looking at the results. Anyway, let's see what he says.
As required by the conservation of angular momentum. If the detectors measure along different directions, the particles only have opposite signs 1/3 of the time. That's a total probability of 5/9, or 55.6%.
Okay.
That's a total probability of 5/9.
He doesn't explain. Well, what exactly did he just do? He he goes through everything so fast. You're like, he's expecting you to be either a genius. Anyway, so same sign. Opposite sign.
Okay, can you make the video 10 seconds back?
This one?
Yeah, can you start a video?
Direction, the particles always have opposite orientations, as required by the conservation of angular momentum. If the detectors measure along different directions, the particles only have opposite signs 1/3 of the time. That's a total probability of 5/9.
What is he when he goes through this counting? What is he what is he counting? I'm not sure what he's counting.
Yeah. Wait, why do I hear my voice repeating in the video?
Your voice repeating in the video? Oh, because you're watching my stream and you're I guess I'm streaming my entire desktop. So you can hear yourself and you can hear me twice probably.
Or 55.6%. If quantum mechanics only represents our ignorance, then entangled particles will have opposite signs in this experiment 55.6% of the time. But that's not what we get when we do the experiment.
I don't understand what he's saying. You can kill me if I understand what he just said.
When we go through and do this thousands of times, we get exactly 50%. Entangled particles have opposite signs in this experiment exactly 50% of the time. Isn't that close enough? Nope, not this time.
But 50%, that sounds like a flip of a coin. It sounds like they're disentangled.
Oh no, what does quantum mechanics predict? It predicts exactly 50%. As we saw earlier, the quantum entanglement looks like this. We can also write it like this, or better yet, like this, since A measures up and down.
So this says the probability of us measuring in the A direction and getting positive, given that it's actually negative. I don't know. He's not explaining any of this.
In quantum mechanics, probabilities are complex squares. So the probability of getting opposite signs when measuring along different directions would be written like this.
I don't even know what this means. This is in the negative direction, measuring A. But this is just A and B. Where's C?
And here's where an author would say something like, the details are a ton of work, which you can see right here. But that's so not my style. After a ton of work.
So psi is this, the probability is this squared, but why is there only A and B? He doesn't explain any of this. This is like, you have to understand it.
Which you can see right here, we get exactly 1/2 or 50%. 50% does not equal 55.6%. Quantum mechanics reigns supreme.
Yeah, he didn't explain anything. Quantum mechanics reigns supreme, and he didn't explain anything. Really nice of him.
But what does this all mean? It means classical physics is a goner. Just put a fork in it. But what this means for quantum mechanics is a bit more nuanced. Locality is the idea that each point in space can only affect its immediate surroundings. So any distant influence must travel through the intervening points in space. Does Bell's experiment mean that entangled particles can interact faster than light? Yes, it does. Our classical understanding of locality is done. It can't possibly be true. Does that mean superpositions are a real physical thing? Not necessarily. It's possible that entangled particles are just connected by a wormhole. It's possible that quantum wave functions don't actually describe the particles, but just describe the new force, some quantum force, that affects what the particles do. It's possible that all outcomes of every circumstance exist in a quantum multiverse, and we just don't know what universe we're in until the experiment is done. What we know for sure is that Bell's experiment shows us that we need to relax our expectations. Thanks for liking and sharing this video.
Anyway, he doesn't explain it. But as you saw in the end,
Mm.
you saw where it takes him. He says either you believe in the multiverse, or you believe in wormholes. I mean, most of the greatest physicists today believe in the multiverse.
Yeah, but I still don't get the answer. Like, if you like look at the moon, then you put the moon behind your back. I mean, the question is, does the moon still exist? I mean, after I turn my back.
So what he's trying to show, the question is, you have a positron and an electron, and they're spinning, but you don't know in which direction. So the question is, do they have a direction or do they not have a direction? Does the moon exist when you're not looking, or does the moon not exist when you're not looking? The question is, does a spinning particle, does it spin in a specific direction when you're not measuring, or does it not spin in any direction? Does it spin in every direction, or is it in a superposition when you're not measuring it? That's the question that is being asked. Which,
Yeah, but don't you think the moon still exists because it's following like the laws of nature, because it's spinning around the sun and stuff
but
like that?
you heard what he said. He said that that's impossible. He said if you believe that particles have an actual existence before you measure them, meaning if you think the moon exists when you're not looking at it, then you're wrong. That's impossible. That is what he said. He said, then if that were true, then you should get 55% in that experiment, but you don't. You get 50%. 50% means that the moon is not there when you're not looking. The moon is only there, or there's. You heard what he said. This guy,
Yeah,
he. Mhm.
yeah, but it's still kind of confusing because I don't know. I don't
Well,
know.
so I agree. I don't think it's confusing. I think it's wrong. The fact that he was able, it's not him. I mean, this is Bell. This is the Nobel Prize for 2022. So 3 years ago, or 2 years ago, they gave the Nobel Prize to scientists who proved everything he just explained. That this thing with the 50 versus 55%, they gave a Nobel Prize for this. This experiment that he just explained, this is the Nobel Prize of 2022. This is what physicists believe. They believe that the moon is not there when you're not looking. And they have proof.
Well, I don't know. Like I told you, I don't believe in a lot of scientists and physicists because some of them like
Yes, I
some
agree.
of them.
Einstein is on your side, but they gave a Nobel Prize to someone who disproved this claim. So physicists, I agree with you. I'm on your side. I think it's It's lunacy. I think it's terrible that this is the state of physics, but this is what they believe, and you can't stop them. This is they run the world. So you ask me why I care. I can't sleep at night because of this. This is driving me insane. That there's people who run the world. These are the physicists. These are the greatest scientists that we have, and they believe this. They believe this nonsense.
What do they believe in?
They believe in Bell's inequality. They believe that the moon is not there when you're not looking. They believe that a particle doesn't have a state when you're not measuring it. It is in a superposition. The particle itself is fuzzy. The particle itself is fuzzy as long as you don't measure it. So
That's fair. It's like all they know at the moment.
no, it's not about knowing. This is what they claim. This is their conclusion. They have proof. They have mathematical proofs. It's not that they don't know the state of the particle. They believe that the state of the particle is a superposition. They believe the moon is in a superposition when you're not looking. They believe
They don't believe that.
Yes, they do. They believe the cat is
They
both.
do not.
Yes, they do. They believe the cat is
Okay,
both.
the superposition is when like some kind of quantum state,
No.
or some, what do they call it? A quantum wave is
No. No,
hasn't
no.
collapsed, right? Well,
No.
in the moon, all the particles are
No.
interacting with each other.
No. Not what I believe. They believe. I'm on your side. This is what they believe. This is the Nobel Prize for 2022. Bell's inequality is the Nobel Prize in physics in 2022. This is what physicists believe, that the moon is not there when you're not looking. Mr. Skyvy. Saddam.
Debunked this guy like
What?
numerous times.
What?
I would have debunked this guy numerous times.
I did not understand what you just said. Your audio is cutting in and out. What did you say?
I've debunked this guy multiple times.
You debunked me?
Saddam Hussein's a troll. Everybody's calling him a troll after the CIA go into.
A troll? Identify troll.
Identify troll. Wait, Saddam Hussein, you debunked me multiple times?
This side guy debunked.
Okay.
Dude, I don't see anything about whatever you just said, that like a moon doesn't exist or whatever. Like I looked it up in ChatGPT what Bell's inequality is. Like gave it to me in the layman's term, it gave it to me in a more technical explanation. It seems to be talking about quantum entanglement between the spins of particles. But isn't that simply just the idea that a spin of a particle is literally just like unknown, and it can only be if another particle is tied to it, and you figure out the quantum spin of one particle, you automatically know the spin of the other particle, even though that other particle can be a gajillion light years away.
Nobody knows what the fuck you're talking about, bro.
Saddam, I'm going to mute you if you interrupt.
That was it. That was my question.
Right, but Saddam interrupted. Anyway, so right, so when you measure two entangled particles that are far away, you always get opposite spins. So
Exactly.
how does it work?
Yeah, but well, it seems like it's already predetermined, right? Or you just have two particles. One is the one spin, the other is the other spin.
So
And you can correct me if I'm wrong on this, but it seems like they already have their spins, but you don't know until you measure it. But they make a big deal out of it that like, oh, when you measure one particle and the other particle is like trillions of light years away, the information from that other particle like travels to you faster than light, and you get to know what it is, even though it's like on the other side of the galaxy.
Mm-hmm. So that's a violation of of the speed of light. It's supposed to be the maximum speed. So how does that work? How is that possible? So
Because there was some mechanism
but if you
that
think
affected both particles,
fine.
and when you measure the one particle, you automatically know what the other particle's state is, even though you can't observe it.
So right, but you're saying that it's not that the particle had a state, right? You're saying the particle did not have a state until I measured, right?
I'm not saying no. I'm saying like its spin is already determined.
Then why do you need
Isn't okay? So
why do you need faster than light communication? Why do you need any
okay,
communication?
never mind, dude. Whatever.
What? Anyway, maybe I'll go to sleep. Oh my god, yeah, I'm gonna go to sleep. Alright. Very nice. Mm, yeah. Okay, bye.